These are the newest images of 3IATLAS from yesterday, and I'm pretty sure this is actually the most shocking anomaly we've seen about this object, because the only possible explanation until now was that it's breaking apart. But the new images reveal something far stranger, a green glow surrounding the nucleus that appears and disappears, changes intensity, and behaves in ways that no natural comet has ever behaved before. So in this video, I'll break down everything we know about what's actually happening with the green mystery glow of 3IATLAS, because what we're seeing right now challenges every assumption we had about this object. So let's first talk about why everyone was convinced that it should be fragmenting or breaking apart, and then we'll talk about what the newest images actually reveal about this green glow phenomenon. On November 9th, we captured these images showing a tail and a sunward tail extending millions of kilometers. But for comets, gas flows out at only about 1 kilometers per hour. That's pretty slow for space. So for the tails to stretch out millions of kilometers at that speed, the comet would need to be shooting out gas constantly for a couple of months. But images from just a few days earlier showed absolutely no tail at all, which is just one of the weird parts about the tails. The comet would need about 1,600 square kilometers of surface area absorbing sunlight. That's the same as a sphere 23 kilometers across, but Hubble measured 3IATLAS at only 5.6 kilometers across. The math showed us it needed to be 4 times bigger than what it actually was. But here's what makes the new observations so disturbing. Multiple observers between November 11th and November 17th, 2025, captured something unexpected. A distinct green glow surrounding the nucleus, not just a faint tint, a pronounced green coloration that appears in some images and not in others. Observers like Satoru Murata from New Mexico, Efrain Morales from Puerto Rico, and teams from This happens when sunlight breaks apart diatomic carbon molecules, C2, in the coma. The broken carbon atoms emit light at a specific wavelength that appears green to our eyes. This is normal, this is expected, but here's the problem. The green glow in 3IATLAS doesn't behave like normal cometary green emission. It appears and disappears over short time periods. It changes intensity dramatically, and in some images, it appears concentrated in specific regions rather than distributed evenly throughout the coma. This is not how C2 emission works. C2 emission should be relatively stable. It should be distributed throughout the coma based on where the parent molecules are being broken down by sunlight. It shouldn't turn on and off like a light switch. Let's talk about what we're actually seeing in these images. When astrophotographers process the raw data and adjust for color balance, something remarkable appears. The coma surrounding 3IATLAS shifts between different colors over time. Sometimes it appears greenish. Sometimes it appears more orange or reddish. Sometimes it appears pale or almost white. These shifts happen over periods of hours to days, which is far too rapid for normal cometary chemistry. In a typical comet, the color of the coma is determined by the composition of the gases being released. Different molecules emit light at different wavelengths. Water produces a bluish glow. Carbon compounds produce green. Sodium produces yellow-orange. Iron and nickel produce red, but the composition of a comet doesn't change rapidly. If a comet is releasing water vapor, it continues releasing water vapor. The color should remain relatively stable unless the comet's activity changes dramatically or it rotates to expose a different region with different composition. 3IATLAS is doing something different. The color shifts are too rapid and too dramatic to be explained by simple rotation or changing activity levels. Something else is going on. Now let's look at what spectroscopy tells us. Spectroscopy is the technique of splitting light into its component wavelengths to identify what molecules are present. It's like a fingerprint for chemical composition. The James Webb Space Telescope analyzed 3IATLAS and found something unusual. The object has way more carbon dioxide compared to water than normal comets. About 8 times more than the usual ratio. This could be because cosmic rays converted carbon monoxide on the surface into carbon dioxide over billions of years. But here's what's strange about the green glow. If the green color were coming from C2 emission, we should see strong carbon monoxide or other carbon-bearing molecules in the spectrum, and we do see carbon dioxide, but the ratio doesn't quite match what we'd expect for the intensity of green glow observed. Some researchers have suggested that the green glow might not be C2 emission at all. It might be something else entirely. Nickel emission, for example, can produce a greenish color, and we know 3I-ATLAS has unusually high nickel content in its plume, but nickel emission requires very specific conditions. The nickel atoms need to be ionized and then excited by solar radiation. This typically happens in the inner coma, very close to the nucleus. It doesn't explain why the green glow appears to extend far from the nucleus in some images. Let's focus on the time variation of the green glow. This is where things get really strange. Observers have documented the green glow appearing, intensifying, fading, and disappearing over periods as short as a few hours. In one sequence of images taken over a single night, the green glow was barely visible at the start of observations. 3 hours later, it had intensified significantly. By the end of the night, it had faded again. This kind of rapid variation is extremely difficult to explain with natural processes. C2 emission depends on the rate at which parent molecules are being broken down by sunlight. That rate should be relatively stable over short time periods, unless something dramatic changes. What could cause such rapid changes? One possibility is that 3I-ATLAS is rotating and exposing different regions with very different compositions. But we know the rotation period is about 16 hours. The color changes we're seeing happen faster than that. Another possibility is that the activity level is changing rapidly. Maybe jets are turning on and off as different regions rotate into sunlight, but that still doesn't explain why the color changes so dramatically. Different activity levels should change the brightness, not the color. Now let's talk about where the green glow appears. In some images, it's distributed relatively evenly throughout the coma. This is what we'd expect for normal C2 emission. The parent molecules are released from the nucleus, they drift outward, and they're broken down by sunlight throughout the coma. But in other images, the green glow appears concentrated in specific regions. Sometimes it's brighter on one side of the nucleus. Sometimes it appears in patches or clumps. Sometimes it seems to follow the jets. This patchy distribution is hard to explain. If the green glow is C2 emission, it should be relatively smooth and symmetric, unless there are very strong directional jets. And while 3I-ATLAS does have jets, they don't always correlate with where the green glow appears. Some observers have noted that the green glow sometimes appears brighter in the forward-facing jet, the one pointing toward the sun. This is particularly strange because that jet also shows a reddish hue in some images. How can the same region appear both green and red? The answer might be that we're seeing multiple emission processes happening simultaneously. The red color could be from dust particles or nickel emission. The green color could be from C2 or some other molecule. But that still doesn't explain why the green glow varies so rapidly. Given all these anomalies, some researchers have proposed a radical explanation. Maybe the green glow isn't chemical emission at all. Maybe it's plasma emission. Plasma is the fourth state of matter, a gas that's been heated or energized so much that electrons are stripped from atoms, creating a soup of charged particles. Plasma can emit light at various wavelengths depending on what elements are present and how energized they are. In space, plasma structures can form and maintain themselves through electromagnetic interactions. The solar wind is a plasma. The Earth's aurora is caused by plasma, and some researchers have suggested that 3I-ATLAS itself might be a plasma entity, or at least surrounded by a plasma sheath. If the green glow is plasma emission, it would explain the rapid variations. Plasma can respond very quickly to changes in the electromagnetic environment. As the solar wind fluctuates or as 3I-ATLAS moves through regions with different magnetic field strengths, the plasma could brighten or fade. It would also explain the patchy distribution. Plasma structures can be highly organized and localized. They don't spread out evenly like gas molecules do. They follow magnetic field lines and can form filaments, sheets, or clumps. But this hypothesis has problems too. For plasma to emit visible light, it needs to be very energized. Where is that energy coming from? Solar radiation alone typically isn't enough to create bright plasma emission at the distances we're talking about. Now let's consider the technological hypothesis. If 3I-ATLAS is an artificial object, a probe sent by another civilization, how would that explain the green glow? One possibility is that the green glow is a byproduct of propulsion. If the jets we're seeing are actually thrusters, they might be expelling ionized gas that emits light. The color would depend on what propellant is being used. Xenon ion thrusters, which we use on some of our own spacecraft, produce a blue glow, but other propellants could produce different colors. A nickel-based propellant, for example, might produce a greenish glow. The rapid variations would make sense if the thrusters are being fired intermittently. Turn them on, the glow appears. Turn them off, it fades. The patchy distribution would make sense if there are multiple thrusters in different locations. But this raises questions too. Why would an advanced civilization use thrusters that produce such a visible glow? Wouldn't they want to be stealthy? Unless, of course, they don't care about being detected. Or maybe they want to be detected. Another technological possibility is that the green glow is some kind of sensor or communication system. Maybe it's a scanning beam or a signal. The variations in intensity and location could represent data transmission or active scanning of the environment. This sounds like science fiction, but if we're seriously considering the possibility that 3IATLAS is artificial, we have to think about what an artificial object might do and what signatures it might produce. So what do we actually need to figure this out? First, we need high-resolution spectroscopy of the green glow. We need to identify exactly what wavelengths are being emitted. That will tell us whether it's C2, nickel, some other element, or a combination. Second, we need time-resolved observations. We need to watch the green glow continuously over hours or days to understand exactly how it varies. Does it pulse? Does it flicker? Does it follow a pattern? Third, we need polarization measurements. Light from plasma has different polarization properties than light from chemical emission. Measuring the polarization of the green glow could tell us whether it's plasma or chemistry. Fourth, we need to correlate the green glow with other observables. Does it brighten when the jets are active? Does it respond to changes in the solar wind? Does it correlate with the object's rotation? And fifth, we need to compare 3IATLAS to other comets. Have we ever seen anything like this before? Are there any historical observations that might give us clues? The good news is that all of these observations are technically feasible. The bad news is that 3IATLAS is getting fainter as it moves away from the Sun. The window for detailed observations is closing. Let's think about what each explanation would mean. If the green glow is normal C2 emission that just happens to vary more than usual, it tells us that cometary chemistry can be more dynamic than we thought. That's interesting but not revolutionary. If the green glow is plasma emission from a natural plasma structure, it tells us that space plasmas can create organized, visible structures that we haven't fully appreciated before. That would be a significant discovery in plasma physics. If the green glow is a byproduct of artificial propulsion or technology, it tells us that we're not alone and that another civilization has achieved interstellar travel. That would be the most important discovery in human history. The stakes are high, and that's exactly why we need to investigate this thoroughly and transparently. We can't dismiss anomalies just because they're uncomfortable. We can't jump to conclusions just because they're exciting. We need to follow the data wherever it leads. The green glow is just one piece of a larger puzzle. Remember, 3IATLAS has multiple anomalies that don't fit the natural comet explanation. It has a retrograde trajectory aligned with the ecliptic plane. It has jets pointing toward the Sun. It has a perpendicular jet confirmed by the Mars Reconnaissance Orbiter. It has unusually high nickel content and almost no water. It has extreme negative optical polarization never seen before. It has non-gravitational acceleration, suggesting massive mass loss without a visible debris cloud. It has collimated jets that maintain orientation despite rotation, and it survived perihelion intact when it should have fragmented. Now add the green glow that appears and disappears, changes intensity, and shows patchy distribution. Each anomaly on its own might be explainable, but together they form a pattern that simply doesn't fit any natural explanation we have. This is why some scientists are taking the technological hypothesis seriously. Not because they want it to be true, not because they're jumping to conclusions, but because the data is forcing them to consider possibilities they would normally dismiss. So what happens now? 3IATLAS is moving away from the Sun and getting fainter. Within a few weeks, it will be too faint for most telescopes to observe. We have a limited window to gather more data. Professional observatories need to prioritize observations of 3IATLAS. Every night of telescope time counts. Every spectrum, every image, every measurement adds to our understanding. Amateur astronomers should continue their incredible work. The images they're capturing and sharing openly are invaluable. They're documenting phenomena that might otherwise go unnoticed, and the public needs to demand transparency. If there are observations being made that aren't being shared, we have a right to know why. This isn't a discovery for a select few. This is a discovery for all of humanity. We also need to start thinking about follow-up missions. If 3IATLAS is still within reach, we should seriously consider sending a probe to intercept it. We have the technology. The question is whether we have the will. Folks, something is seriously wrong with the 3IATLAS green mystery glow. It appears and disappears. It changes intensity over hours. It shows patchy distribution that doesn't match normal cometary emission. And it's just one of many anomalies that make this object unlike anything we've seen before. We have three main explanations on the table: unusual but natural cometary chemistry. If there are observations being made that aren't being shared, we have a right to know why. This isn't a discovery for a select few. This is a discovery for all of humanity. We also need to start thinking about follow-up missions. If 3IATLAS is still within reach, we should seriously consider sending a probe to intercept it. We have the technology. The question is whether we have the will. Folks, something is seriously wrong with the 3IATLAS green mystery glow. It appears and disappears. It changes intensity over hours. It shows patchy distribution that doesn't match normal cometary emission. And it's just one of many anomalies that make this object unlike anything we've seen before. We have three main explanations on the table: unusual but natural cometary chemistry, plasma emission from a natural or artificial plasma structure, or a technological signature from an artificial object. None of these explanations is proven. All of them deserve investigation. What we know for certain is that the green glow is real, it's anomalous, and it demands an explanation. The next few weeks are critical. As 3IATLAS fades from view, we're losing our chance to study it in detail. If we don't act now, we might never know what this object really is. And that would be a tragedy. Because whether 3IATLAS is an exotic comet, a plasma phenomenon, or an artificial probe, it represents something extraordinary. Something that could change our understanding of the universe and our place in it. If you watch to the end, drop me a like and subscribe for more updates. And click on the video appearing on your screen right now, where we break down the plasma hypothesis in detail and explain exactly how a plasma entity could produce the behaviors we're seeing. I'll see you in the next one.